So we're talking about single slit diffraction here. And actually this is something that I had observed as a kid and never knew exactly what was going on. Assuming that you have sort of cracks between your fingers right there, if you hold your fingers up and you sort of hold it towards the light, and you'll notice that there's these dark fringes in the corners. So if you're looking at the gap between your fingers there's some dark fringes along here. That's the result of single slit diffraction. As a kid, I thought it was just tiny little hairs or something like that. Good thing I became educated. So we have the single slit diffraction, and it's very similar, sometimes too similar. It's very similar to double slit. So if we think about wave propagation, what Huygens originally had considered is that if I have a wave right here, that each point on this wave actually produces a new wave. So if I have a wave here, then it's producing waves, and that produces waves, and that produces waves, and that produces waves. And if you add those up, that it end up looking like that. But each point on the wave actually produces a wave in and of itself. And so that is sort of the big thing in terms of the wave property over here. So if I have a single slit here, and the distance, the width of this is capital D. This is a tradition that I've noticed that capital D would represent the width of the slit, and lowercase d is the distance between slits for double slit or diffraction grating. So I have a point here, I have all sorts of these points here that are all producing waves. So if I have a screen over here, then, well, let's think about what's going on there. Let's say that I have some point here where the points on the extremes are actually would produce a bright spot. In other words, the extremes, let's move that dot there. I'm having difficulty drawing lines today. All right, so if the points at the end would produce a bright spot, we don't actually see a bright spot. Because if we think about that, and I'm going to try to draw that a little bit straighter. You can marginally say it's straighter, not a whole lot. If these would produce a bright spot, that means that these are a wavelength apart. So the distance here, if this is R1, this is R1 to this point right here. And this right here is, let's just say, a wavelength apart. So our R2, using our notation earlier, R2 plus the R1 plus the wavelength is equal to R2. So the deal is, though, is that if that is a wavelength apart, then if I'm halfway to here, if I look at the point creating a wave at this point, at this spot, that would be a half wavelength apart, which means that these two would produce destructive interference and it would produce a dark spot. So these 2 points produce a bright spot, but these 2 points produce a dark spot. So what is actually going to win out? Well, if this is a wavelength apart, that means that this point right here and this point right here would also produce a dark spot. This point right here and this point right here would also produce a dark spot. That point right here and that point right there would also produce a dark spot. Matter of fact, we have far more things creating dark spots than we have producing light spots. There's far more destructive interference than there is constructive interference. So what we end up with, as the textbooks generally say, it's not a dark spot, they call it a minima. In other words, the less bright spot. There is one little bit of light showing up there, although it's too small, and usually with the human eye, it looks dark. So, if we just adapt the formula that we had for the double slit, so for double slit, we had that the sine of theta was equal to lambda over d. For the first bright spot, this is for the first bright spot, or first bright spot. Then we are now looking at that for the first dark spot. So for single slit, sine of theta is going to be equal to lambda over d to produce for first dark spot. And we can then generalize it. So for the single slit, for the dark spots, sine of theta is equal to m lambda over capital D. So we now have the position of dark spots. So what would happen if we're showing through a double slit? Well, if I have a double slit here, I basically have two single slits. So not only do I have the double slit interference pattern happening, as described by this, but I have a single slit diffraction pattern also happening by the same token, or interference pattern. And so the single slit would produce a bright spot and then a darker spots. The double slit basically produces far more frequency there, would produce a bright spot So the single slit creates what's called an envelope. This is a single slit envelope. And there would be a double slit pattern sort of mixed in there. So I'm going to put the camera on pause. I'm going to set it up so that we can actually see that.